600 light-years away floats a world that captured humanity's imagination the moment scientists announced its discovery. Kepler-22b orbits within the habitable zone of a sun-like star, suggesting liquid water might pool on its surface. Headlines declared we had found Earth's twin. Space agencies began dreaming of missions. Artists rendered lush oceans and alien continents. But here is the terrifying truth nobody wants to discuss. We have no idea what this planet actually is. We do not know its mass. We cannot determine if it has a surface. We cannot confirm whether it is rocky, gaseous, or something in between. Every mission timeline you have ever heard assumes we know where we are going. We do not. The destination itself remains undefined. If you enjoy journeys that challenge everything you thought you understood about space exploration, consider hitting that like button and subscribing to the channel. Your support helps us continue exploring these cosmic mysteries together. Now get yourself comfortable. Let's begin. The announcement came on December 5th, 2011. NASA scientists stood before cameras and revealed that humanity had found something extraordinary. A planet orbiting within the habitable zone of a star remarkably similar to our Sun. The world carried the designation Kepler-22b, named for the spacecraft that detected it, and the star it orbits. Within hours, the discovery dominated headlines worldwide. Artists produced stunning visualizations showing a blue marble hanging in space, continents emerging from global oceans, clouds swirling across temperate skies. The imagery suggested we had found Earth's twin, a world where humans might one day walk beneath an alien sun that looked almost identical to our own. News anchors spoke of breakthrough discoveries. Science journalists described habitable conditions. Online forums erupted with speculation about alien life and future colonization. The narrative crystallized almost immediately into something clean and compelling. We had found another Earth. But here is what those breathless announcements did not explain. We did not actually see this planet. We detected a shadow. The Kepler Space Telescope launched in March 2009 with a singular mission. It would stare at approximately 150,000 stars simultaneously, watching for tiny dips in brightness that might indicate planets crossing in front of their host stars. This technique, called the transit method, revolutionized exoplanet detection. Before Kepler, humanity had confirmed only a few hundred worlds beyond our solar system. By mission's end, that number would climb into the thousands. The transit method works on a beautifully simple principle. When a planet passes between its star and our telescopes, it blocks a small fraction of the starlight. For a planet the size of Jupiter crossing a sun-like star, this dimming measures roughly 1%. For an Earth-sized world, the dimming drops to approximately 1/100th of 1%. Detecting such tiny variations requires instruments of extraordinary precision and patience, spanning years of continuous observation. Kepler achieved this precision through unwavering dedication to a single patch of sky. The spacecraft fixed its gaze on a region in the constellation Cygnus, containing roughly 150,000 target stars. It watched these stars continuously, measuring their brightness every 30 minutes, accumulating data that would eventually reveal thousands of planetary candidates. The mathematics of transit detection required patience that stretched human attention spans to their limits. A planet must cross directly between its star and Earth for us to observe a transit. This geometric alignment occurs for only a small fraction of planetary systems. Even when alignment exists, we must wait for the planet to complete its orbit and cross again to confirm the detection. Kepler-22b first crossed in front of its star on May 12, 2009, just days after Kepler began scientific operations. But one transit proves nothing. Stars vary in brightness for countless reasons. Sunspots rotating across stellar surfaces create periodic dimming. Stellar oscillations produce rhythmic brightness changes. Binary companion stars create eclipses that mimic planetary transits. Instrumental artifacts generate false signals in the data. A single dimming event could mean almost anything. Scientists needed to see the pattern repeat. They needed multiple transits occurring at regular intervals to confirm that something was genuinely orbiting the star. For Kepler-22b, with its orbital period of approximately 290 days, this meant waiting nearly 2 Earth years between crossings. The second transit occurred in late February 2010. Scientists noted the event but required additional confirmation. The third transit came in December 2010. By this point, Kepler's data processing pipeline demanded months of careful analysis to confirm the detection. The team needed to rule out false positives, verify the signal against instrumental effects, examine the light curve shape for signs of contamination, and calculate the orbital parameters with sufficient precision to announce a discovery. False positive scenarios required particular attention. A background eclipsing binary star could produce transit-like signals if its light blended with the target star. A grazing eclipse by a stellar companion could mimic a planetary transit. Even instrumental effects could create periodic signals that fooled initial analysis. Each possibility demanded investigation before announcement. When confirmation finally came in late 2011, the scientific community celebrated. Here was a world orbiting in the habitable zone of a G-type star, the same stellar classification as our Sun. The orbital period of 289.8 days meant the planet received stellar energy comparable to what Earth receives. Everything about the discovery seemed to scream that we had found something special, but celebration obscured a crucial reality. The transit method reveals almost nothing about what a planet actually is. When Kepler-22b crossed its star, it blocked approximately 0.05% of the starlight. From this single measurement, scientists could calculate one and only one property with reasonable confidence. The planet's radius measured approximately 2.1 times larger than Earth. That is it. That is everything the transit told us about this world's physical nature. 2.1 Earth radii, a number that sounds precise and scientific, a number refined through careful analysis of transit depth, limb darkening corrections and stellar radius estimates, a number that actually tells us almost nothing useful for planning any kind of mission. Consider what this measurement means. We know the planet casts a shadow roughly 2.1 times wider than Earth's shadow would be. We do not know what creates that shadow. We do not know if it comes from rock, gas, liquid, ice, or some combination we have never encountered. The precision of the radius measurement creates an illusion of comprehensive knowledge. Scientists can quote 2.1 Earth radii with confidence intervals and error bars. They can discuss the measurement uncertainty with mathematical rigor, but precision in one measurement does not translate to knowledge of the planet itself. We measured one thing very well. That one thing tells us almost nothing about what kind of world exists. This brings us back to the real problem that haunts every discussion of traveling to Kepler-22b. We cannot plan a mission to a destination we cannot define. Think about what mission planning requires. Engineers need to design landing systems, which demands knowing whether a surface exists and what it is made of. They need to calculate fuel requirements for orbital insertion and landing, which requires knowing the planet's mass and gravitational pull. They need to design heat shields and atmospheric entry systems, which means understanding what kind of atmosphere exists and how thick it might be. They need to plan surface operations, which requires understanding temperature ranges, radiation environment, and terrain characteristics. We have none of this information for Kepler-22b. We have a shadow measurement and a location in space. Everything else is speculation dressed in scientific terminology. The star itself, Kepler-22, offers some context but no salvation from uncertainty. This G-type dwarf star sits approximately 640 light-years from Earth in the constellation Cygnus. Its spectral classification of G5 places it slightly cooler than our Sun, which carries a G2 classification. The surface temperature measures around 5500 Kelvin compared to the Sun's 5778 Kelvin. Its luminosity runs about 79% of solar output. These stellar properties allow scientists to calculate the habitable zone boundaries where liquid water might theoretically exist on a planetary surface. The habitable zone concept defines a range of orbital distances where temperatures could potentially support liquid water given certain atmospheric assumptions. Too close to the star and water boils away. Too far and water freezes solid. The habitable zone marks the theoretical sweet spot between these extremes. Kepler-22b orbits comfortably within this zone, closer to the inner edge where temperatures would be warmer but still potentially hospitable. The orbital distance places it in a region analogous to where Venus and Earth orbit our Sun, though the lower stellar luminosity shifts the habitable zone inward compared to our solar system, but the habitable zone represents a theoretical construct based on assumptions that may not apply. It assumes a rocky planet with an atmosphere similar to Earth's. It assumes plate tectonics and a carbon cycle regulating temperature. It assumes a magnetosphere protecting the surface from stellar radiation. It assumes water exists on the surface in the first place. We have no evidence that any of these assumptions hold for Kepler-22b. The habitable zone calculation also ignores the possibility that this world might not be what we imagine at all. A planet 2.1 times Earth's radius could be many different things. The radius alone constrains almost nothing about composition or structure. It could be a rocky super-Earth with crushing surface gravity and a thick atmosphere producing runaway greenhouse heating. Venus demonstrates that planets within habitable zones can develop surface conditions utterly hostile to life as we know it. Surface temperatures on Venus exceed 460 degrees Celsius despite orbital distances that should allow moderate temperatures. Thick carbon dioxide atmosphere creates greenhouse effects that transform potentially habitable worlds into hellscapes. It could be a mini Neptune with no solid surface at all. The solar system provides no direct analogue for such worlds, but they appear common among exoplanet populations. These planets exist in a size range between Earth and Neptune that our solar system somehow failed to produce. It could be an ocean world with global seas hundreds of kilometers deep and unimaginable pressure at whatever solid floor exists far below. Water worlds might have surfaces entirely covered by liquid ocean, with no continents, no exposed rock, no land of any kind. The pressure at the ocean floor of such worlds would exceed anything terrestrial submarines could survive. Each of these possibilities would require completely different mission architectures. Landing on a rocky super-Earth demands different technology than diving into a mini Neptune's atmosphere. Exploring an ocean world requires capabilities we have never developed. Surviving a Venus-like greenhouse world might be impossible with foreseeable technology. We cannot design spacecraft for all possibilities simultaneously. The transit method's limitations become even more apparent when we examine what additional observations have revealed, or more accurately, what they have failed to reveal. After the initial discovery, astronomers attempted to measure the planet's mass using radial velocity techniques. This method detects the gravitational wobble a planet induces in its host star. As a planet orbits, it tugs the star slightly toward and away from Earth, creating detectable shifts in the star's spectral lines. The star does not remain stationary while its planet orbits. Both bodies orbit their common center of mass, and this stellar motion produces measurable Doppler shifts. For massive planets orbiting close to their stars, radial velocity measurements work beautifully. Jupiter-sized worlds produce wobbles easily detected by ground-based instruments. Hot Jupiters orbiting in days rather than years create signals that repeat rapidly, allowing quick confirmation. But Kepler-22 presents a much more challenging target. Its orbital period of nearly 290 days means the gravitational signal spreads across almost an entire Earth year. Observing campaigns must span multiple years to capture complete orbital cycles. Weather, telescope scheduling, and seasonal visibility all complicate the observations. The star itself creates additional challenges. Kepler-22 shows some level of stellar activity that introduces noise into radial velocity measurements. Star spots, convective motions, and magnetic activity all produce apparent velocity shifts that can mask or mimic planetary signals. Its presumed mass, whatever that might be, produces only tiny stellar wobbles. A planet with mass similar to Earth orbiting at Kepler-22b's distance would induce velocity changes of perhaps 10 centimeters per second in its host star. Current instruments can detect signals of roughly 1 meter per second under ideal conditions. The expected signal falls near or below detection thresholds. Multiple observing campaigns targeted Kepler-22 using precise instruments capable of detecting stellar velocities to within 1 meter per second. The higher spectrograph on the Keck telescope contributed observations. The HARPS N spectrograph provided additional data. Years of careful monitoring accumulated. The results produced upper limits rather than actual measurements. Scientists could say with confidence that Kepler-22b has a mass less than 9.1 times Earth's mass, but they could not determine whether the actual mass was 9 times Earth, 5 times Earth, 2 times Earth, or something else entirely within that range. This upper limit constraint represents the best mass information we have after more than a decade of follow-up observations. The radial velocity campaigns did not fail in any technical sense. They pushed measurement precision to its limits and extracted what information the data contained. But the information content proved insufficient to determine actual mass. We know the planet probably masses less than 9.1 Earths. We do not know where within that range the actual value falls. Without mass, we cannot calculate density. Density equals mass divided by volume. We have volume from the radius measurement. We lack mass from any measurement technique. The density calculation cannot proceed. Without density, we cannot determine composition. Rocky planets have densities around 5 grams per cubic centimeter. Ice-rich planets might have densities around 2 grams per cubic centimeter. Gas-dominated planets show densities below 1 gram per cubic centimeter. Density provides the crucial link between measured size and inferred structure. Without it, composition remains unconstrained. Without composition, we have no idea what kind of world awaits at the end of a 640 light-year journey. The destination remains fundamentally undefined despite years of observation and analysis. The implications cascade through every aspect of mission planning. Consider gravity alone. Surface gravity depends on both mass and radius. According to straightforward physics, a rocky planet with 2.1 Earth radii could have surface gravity ranging from 1.2 to over 3 times Earth's gravity, depending on its internal structure and total mass. Spacecraft designed for 1.2 g would be crushed in 3 g. Structural elements sized for moderate gravity would buckle under forces 3 times higher. Landing legs would collapse. Instruments would be damaged. The entire spacecraft would fail catastrophically if gravity exceeded design parameters. Systems built for 3G would be absurdly over-engineered for 1.2G. Massive structural reinforcement would add weight that could have been used for scientific instruments or additional fuel. The spacecraft would function but perform far below its potential. Resources would be wasted on unnecessary strength. Consider atmosphere. A mini Neptune has no defined surface, just pressure and temperature increasing as you descend through ever-thickening gas until conditions become unsuitable for any spacecraft we could build. Entry vehicles would descend through increasingly dense atmosphere until heat and pressure destroyed them. There would be no landing because there would be no ground to land on. A rocky super-Earth might have an atmosphere ranging from none at all to pressures hundreds of times greater than Earth's surface. Venus has an atmosphere roughly 90 times Earth's surface pressure. Both are rocky worlds. Both have completely different atmospheric conditions. We cannot design atmospheric entry systems without knowing what atmosphere exists. Entry vehicles need heat shields sized for expected heating rates. Heating depends on atmospheric density and composition. Parachutes need sizing for expected atmospheric drag. Drag depends on density and molecular weight. Powered descent systems need thrust levels calibrated to atmospheric resistance. Every element of entry and landing depends on atmospheric knowledge we do not possess. Consider landing itself. An ocean world requires floating platforms or submarines. Spacecraft would need to survive water landing and potentially operate beneath the surface. We have never designed interstellar probes with naval architecture requirements. A rocky world demands legs or wheels depending on terrain characteristics we cannot predict. Surface roughness, slope angles, rock distributions and soil properties all affect landing system design. A spacecraft designed for smooth basalt plains would fail on boulder-strewn terrain. A system designed for rugged mountains would be over-designed for smooth surfaces. A gas-dominated planet provides nothing to land on at all. The spacecraft would simply descend until it was destroyed by increasing temperature and pressure. Mission success would be impossible by definition because no surface exists to reach. Each possibility requires fundamentally different engineering solutions that cannot be combined into a single spacecraft design. This brings us back to the real problem that makes every discussion of reaching Kepler-22b fundamentally misguided. We are not debating how to reach a destination. We are debating how to reach a question mark. The beautiful artist renderings showing blue oceans and Earth-like continents are not scientific illustrations. They are science fiction. They depict one possible interpretation of extremely limited data, an interpretation that may have no relationship to reality. These images serve communication purposes. They help the public visualize discoveries that would otherwise remain abstract numbers. They generate excitement and support for space science. They are not dishonest in intent, but they create impressions that extend far beyond what evidence supports. Scientists know this. The uncertainty appears in every peer-reviewed paper discussing Kepler-22b. Phrases like could be, might have, potentially, and if assumptions hold litter the technical literature, error bars and confidence intervals accompany every quantitative statement. The scientific community maintains appropriate caution about what we actually know, but these qualifications disappear in popular discussions that treat this world as a confirmed Earth twin awaiting human visitors. The careful language of scientific papers transforms into confident statements about habitable conditions and Earth-like environments. The transition from discovery to characterization gets glossed over as if measuring a shadow tells us everything about what cast that shadow. The transit detection that revealed Kepler-22b represents a genuine scientific achievement. Finding a planet-sized object orbiting in the habitable zone of a sun-like star at such enormous distance pushed observational astronomy to remarkable limits. The precision required to detect a 0.05% brightness change repeated over nearly 300-day intervals demonstrates extraordinary instrumental capability. The discovery deserves celebration. Kepler-22b represents one of the first confirmed planets orbiting in the habitable zone of a sun-like star. It expanded our understanding of planetary system diversity. It demonstrated that planets exist in configurations potentially favorable to life as we understand it. The detection itself was masterful, but discovery and characterization are different things entirely. We discovered that something exists at a specific location in space. We have not characterized what that something is. The gap between detection and understanding spans the entire difference between knowing a shadow exists and knowing what casts that shadow. Astronomers discover new objects constantly. Most discoveries require years of follow-up observation to reveal true nature. Initial detection provides coordinates and basic parameters. Characterization requires entirely different observational approaches and often different instruments. The process from discovery to understanding typically spans decades for challenging targets. Kepler-22b ranks among the most challenging targets conceivable. Its distance prevents direct imaging with any foreseeable technology. Its orbital geometry complicates transmission spectroscopy that might reveal atmospheric composition. Its host star's activity introduces noise that masks weak planetary signals. Every characterization approach faces fundamental obstacles. Every calculation of travel time to Kepler-22b, every discussion of generation ships and cryogenic freezing and relativistic propulsion, every imaginative scenario involving human colonists arriving at this distant world, all of it collapses against a single unavoidable truth. We do not know what we are traveling to. The destination does not exist as a defined target. It exists as a probability distribution, a range of possibilities, a collection of maybes that might include anything from a rocky paradise to an uninhabitable gas ball to something completely outside our current understanding. You cannot plan a journey to a probability distribution. Mission planning requires specific parameters. Spacecraft design requires defined conditions. Fuel calculations require known gravity wells. Surface operations require understood environments. Every aspect of mission architecture flows from destination knowledge we do not possess. You cannot design spacecraft for unknown compositions. Material selection depends on expected thermal environment. Structural design depends on anticipated loads. Power systems depend on predicted energy availability. Communication systems depend on assumed signal path characteristics. Every engineering decision requires assumptions about destination conditions that we cannot validate. You cannot calculate fuel requirements for undefined gravity wells. Orbital insertion requires specific velocity changes determined by planetary mass. Landing requires thrust calibrated to surface gravity. Launch from the surface requires energy scaled to escape velocity. Without mass, these calculations produce ranges rather than numbers. The target uncertainty does not merely complicate mission planning. At this stage, it eliminates the possibility of meaningful mission planning altogether. We face a situation where the fundamental prerequisites for mission design do not exist. Before asking how to get somewhere, we must know where we are going in sufficient detail to design systems for arrival. We do not know that for Kepler-22b. We may not know it for decades. We may never know it with available technology. All of this still fails because the target uncertainty represents not a temporary obstacle, but a fundamental limitation of current observational capability. We detected Kepler-22b because it happened to transit its star from our perspective. We cannot characterize it because distance and geometry prevent the observations that would reveal its true nature, and this represents only the beginning of understanding why Kepler-22 remains forever beyond meaningful reach. The problems deepen dramatically when we examine the specific gap between what we measured and what we need to know. The radius tells us shadow size. Mission planning requires mass, composition, atmosphere, surface conditions, and a dozen other parameters we cannot measure. The catastrophe hiding within that 2.1 Earth radii measurement becomes clear only when we understand what that specific number means for planetary composition. At precisely this size, planets could be almost anything. 2.1 Earth radii. This number appears in every scientific paper discussing Kepler-22b, a measurement refined through careful analysis of transit depth, limb darkening corrections, and stellar radius estimates, a number carrying decimal precision and formal uncertainty bounds, a number that creates an illusion of knowledge while concealing a catastrophe. At 2.1 Earth radii, Kepler-22b falls into a size range that planetary scientists have come to regard with something approaching dread, not because planets of this size are rare or uninteresting, but because this specific radius marks the zone of maximum compositional ambiguity in all of planetary science. The Kepler mission discovered thousands of exoplanets, enabling statistical analysis impossible with earlier, smaller samples. When researchers plotted these planets by size and orbital period, a striking pattern emerged. Planets clustered into two distinct populations separated by a gap. Smaller planets with radii below roughly 1.5 Earth radii formed one group. Larger planets with radii above roughly 2.5 Earth radii formed another. Between these populations lay a valley where planets appeared far less frequently. Scientists call this feature the radius valley. Understanding its origin reveals why Kepler-22b's measured size tells us almost nothing about its true nature. The radius valley appears to result from atmospheric loss processes that transform planets over billions of years. Planets born with substantial hydrogen and helium envelopes can lose those atmospheres through various mechanisms. Intense radiation from young stars can heat upper atmospheres until gas escapes into space. Internal heat from planetary formation can drive atmospheric loss from below. The energy released by radioactive decay in planetary interiors can power escape over geological timescales. Planets that lose their primordial atmospheres shrink dramatically. A world that began with 2 Earth radii contracts to 1.5 Earth radii or smaller once its gas envelope disappears, leaving behind a bare rocky core. Planets that retain their atmospheres remain puffy, their hydrogen and helium envelopes contributing substantial volume despite modest mass. The radius valley marks the boundary between these outcomes. Below the valley sit stripped cores, rocky worlds that lost their gas. Above the valley float envelope-retaining planets, worlds that kept their primordial atmospheres. The valley itself contains relatively few planets, because worlds at these intermediate sizes are transitional, either finishing their atmospheric loss or teetering on the edge of retention. Kepler-22b sits not in the valley but just above it at 2.1 Earth radii. This placement means the planet avoided complete atmospheric stripping if it ever possessed a substantial envelope, but it does not tell us whether the planet retained a massive gas layer, lost most of its atmosphere while keeping a thin remnant, or formed as a dense rocky world that never had much gas to lose. The physics underlying this ambiguity involves the relationship between planetary radius, mass, and composition. Radius measures size, mass measures quantity of matter. The ratio of mass to volume yields density, and density constrains what materials a planet contains. Iron has a density of roughly 8 grams per cubic centimeter. Silicate rock runs around 3 grams per cubic centimeter. Water ice measures about 1 gram per cubic centimeter. Hydrogen and helium at planetary interior pressures contribute even less density per unit volume. A planet's bulk density reveals which materials dominate its composition. But density requires both mass and radius. We have radius for Kepler-22b. We lack mass. Without mass, we cannot calculate density. Without density, we cannot constrain composition. The measurement chain breaks at its second link, leaving everything downstream inaccessible. The mathematical relationship illustrates the problem starkly. Density equals mass divided by volume. Volume scales with the cube of radius. For Kepler-22b with radius 2.1 times Earth, the volume measures roughly 9.3 times Earth's volume. If the planet has Earth-like density of 5.5 grams per cubic centimeter, its mass would be roughly 9.3 Earth masses. If it has density of 2 grams per cubic centimeter suggesting substantial ice or gas content, its mass would be only 3.4 Earth masses. The same radius accommodates masses differing by nearly a factor of 3. This range spans the difference between a dense super-Earth with crushing surface gravity and a puffy mini-Neptune with no surface at all. The same shadow measurement permits either interpretation. Transit photometry cannot distinguish between them. Understanding why mass measurement has failed for Kepler-22b requires examining the techniques available and their limitations at this distance. Radial velocity observation remains the primary method for measuring exoplanet masses. The technique exploits Newton's third law. When a planet orbits a star, the planet's gravity pulls the star in a small counter-orbit around the system's center of mass. This stellar wobble produces Doppler shifts in the star's spectral lines, alternately blue shifting and red shifting as the star moves toward and away from Earth. The amplitude of the stellar wobble depends on planetary mass, orbital distance, and stellar mass. More massive planets produce larger wobbles, closer orbits produce larger wobbles, less massive stars wobble more for a given planetary mass. By measuring the wobble amplitude and combining it with known orbital parameters, astronomers can calculate planetary mass. For Kepler-22b, every factor conspires against successful measurement. The planet orbits at a distance, producing an orbital period of 290 days. This means the stellar wobble signal repeats roughly once per Earth year. Observing campaigns must span multiple years to capture complete orbital cycles and build statistical significance. Weather, telescope scheduling, and seasonal visibility all interrupt observations. Assembling enough data points requires patience measured in years, and telescope time measured in dozens of nights. The expected wobble amplitude depends on the planet's unknown mass. If Kepler-22b masses 9 Earth masses, it would produce a stellar velocity variation of roughly 2 meters per second. If it masses 3 Earth masses, the variation drops below 1 meter per second. The expected signal hovers at or below detection thresholds regardless of which mass assumption proves correct. The host star itself complicates matters. Kepler-22 shows evidence of stellar activity, including star spots and convective motions that produce apparent velocity variations unrelated to planetary gravity. These stellar noise sources can mimic, mask, or distort genuine planetary signals. Distinguishing the planetary wobble from stellar jitter requires sophisticated modeling that introduces its own uncertainties. Multiple observing campaigns targeted Kepler-22 with the world's most precise instruments. The Hires instrument on the Keck telescope contributed observations. The HARPS N spectrograph at the Telescopio Nazionale Galileo provided additional data. Teams accumulated observations spanning years of patient monitoring. The results established only an upper limit. With 95% confidence, Kepler-22b masses less than 9.1 Earth masses. The data could not determine whether the actual mass was 9 Earth masses, 5 Earth masses, or 2 Earth masses. The signal remained buried in noise, detectable as an upper bound but not as a specific value. This outcome represents success within the limitations of current technology. The observations pushed instrumental precision to its limits and extracted all information the data contained. The measurements did not fail through error or incompetence. They succeeded in establishing constraints while falling short of definitive detection. The universe simply did not cooperate in providing a measurable signal. Alternative mass measurement techniques offered theoretical hope, but practical disappointment. Transit timing variations arise when multiple planets in a system gravitationally perturb each other's orbits. The perturbations cause transits to occur slightly early or late compared to predictions assuming a single planet. The pattern of timing deviations reveals the masses of the interacting planets without requiring radial velocity detection. For this technique to work, additional planets must exist in the system and produce measurable gravitational effects on Kepler-22b's orbit. Scientists searched the Kepler data exhaustively for evidence of additional transiting planets or timing variations suggesting non-transiting companions. Neither search yielded positive results. The Kepler-22 system appears to contain only one detected planet. Perhaps additional planets exist in non-transiting geometries, but if so, they are too distant or too small to produce detectable gravitational signatures. Direct imaging offers another theoretical approach. If a planet can be observed directly, separated from its star's overwhelming glare, spectroscopic analysis of the planet's light can reveal atmospheric composition and potentially constrain mass through atmospheric scale height measurements. But Kepler-22b orbits far too close to its star for current direct imaging technology. The angular separation between planet and star as viewed from Earth measures mere milliarcseconds. This angle falls far below the inner working angle of any current coronagraph or starshade concept. The contrast ratio between star and planet presents additional obstacles. Kepler-22 outshines its planet by factors of billions in visible light. Detecting the planet requires suppressing starlight by 10 orders of magnitude, while maintaining sensitivity to the faint planetary signal. Current technology achieves contrasts of perhaps 100 million to 1 under ideal conditions. The required improvement spans at least 2 additional orders of magnitude. Every pathway to mass measurement encounters fundamental obstacles that current and near-future technology cannot overcome. The mass we need remains unmeasurable, with existing instruments or any instruments under serious development. This situation will not change within any reasonable planning horizon. The engineering consequences of this measurement failure cascade through every aspect of hypothetical mission design. Consider the challenge of structural engineering without known gravitational loads. Every structural element in a spacecraft must be sized to withstand expected forces during launch, transit, and arrival operations. Launch loads are known quantities determined by the selected launch vehicle. Transit loads depend on acceleration profiles and spacecraft configuration. Arrival loads depend on the destination's gravitational environment. For Kepler-22b, arrival loads cannot be calculated because gravity cannot be calculated because mass remains unknown. Surface gravity scales with mass divided by radius squared. For a planet with 2.1 Earth radii, surface gravity could range from roughly 1.1 Earth gravities to roughly 3 Earth gravities depending on mass within the upper limit constraint. Structural elements sized for 1.1 Earth gravities would collapse under 3 Earth gravities. The safety factors engineers typically apply cannot span a threefold uncertainty range without producing absurdly overbuilt systems. A structure designed to survive 3 gravities with appropriate safety margin would mass 3 to 4 times more than a structure designed for 1.1 gravities. This mass penalty propagates through entire spacecraft design, reducing payload capacity, increasing propellant requirements, and extending journey times. But even designing for the worst measured case fails to guarantee success. The upper limit of 9.1 Earth masses represents a statistical constraint, not an absolute bound. A 5% probability exists that the true mass exceeds this limit. For a mission costing billions of dollars and decades of travel time, 5% failure probability from a single parameter uncertainty alone might be unacceptable. Propulsion system design faces analogous challenges. Orbital insertion requires velocity changes calculated from the target body's gravitational parameter. Unknown mass means unknown gravitational parameter means incalculable orbital insertion requirements. A spacecraft arriving at Kepler-22b with propellant budgeted for a 5 Earth mass gravitational field would find itself critically short. If the planet mass is 9 Earth masses, the velocity change required for orbit capture scales with the square root of planetary mass. A 9 Earth mass planet requires roughly 35% more velocity change than a 5 Earth mass planet for equivalent orbital parameters. Running out of propellant during orbit insertion means either missing the planet entirely or plunging uncontrollably toward whatever surface or atmosphere exists. Thermal control design requires knowing the radiation environment, which depends partly on atmospheric properties that remain unknown. Communication system design requires knowing signal path characteristics through any atmosphere that might exist. Power system design for surface operations requires knowing daylight cycles determined by axial tilt and rotation period, neither of which we have measured. The chain of dependencies extends indefinitely. Each spacecraft subsystem requires information derived from planetary properties we cannot measure. Each uncertainty compounds with others to produce mission architectures built on foundations of assumption rather than knowledge. The traditional engineering response to uncertainty involves designing for worst-case conditions with appropriate safety margins. This approach works when worst cases can be defined. For Kepler-22b, the worst case itself remains uncertain. Is the worst case a high-mass rocky planet with extreme surface gravity, or a low-mass gas-dominated planet with no surface to land upon? These scenarios require completely different designs with no overlap in optimal solutions. The worst case for a landing mission differs fundamentally from the worst case for an atmospheric probe mission. Without knowing which mission type is appropriate, worst-case design becomes conceptually incoherent. The problem resembles being asked to pack for a trip without knowing whether the destination is a beach resort, a mountain glacier, or a submarine base. You cannot pack for all possibilities within reasonable luggage constraints. You must choose, and choosing requires knowledge that the question asker has not provided. Mission designers sometimes address uncertainty through adaptable or modular systems capable of reconfiguration based on conditions encountered. This approach has merit for missions within our solar system where communication delays permit remote guidance, and destinations are known well enough to bound the range of conditions possible. For Kepler-22b, neither condition applies. Communication delays at 640 light-years preclude any real-time guidance. Round-trip signal time exceeds 1200 years. Any adaptation must be autonomous, built into spacecraft systems before launch. But building in adaptability requires anticipating the range of conditions requiring adaptation. For a planet that might be rocky or gaseous or oceanic or something else entirely, the required adaptability approaches complete reconfigurability, which is to say it approaches impossibility. The radius mass degeneracy ensures that this situation will persist until measurement techniques advance far beyond current capability. The mass that would resolve ambiguities about composition requires detecting signals that current instruments cannot extract from noise. The alternative measurement pathways are blocked by unfavorable geometry, absent planetary companions, or insufficient angular resolution. Perhaps 30-meter class telescopes will achieve the radial velocity precision needed to detect Kepler-22b's stellar wobble definitively. Perhaps advanced interferometric techniques will enable direct imaging at milliarc-second separations with 10 billion to 1 contrast. Perhaps some yet unimagined technique will open new pathways to mass measurement. But these possibilities remain speculative. The telescopes are under construction but not yet operational. The techniques are proposed but not yet demonstrated. The timeline for definitive mass measurement stretches to decades optimistically. By the time we might know what Kepler-22b actually is, generations of scientists will have come and gone. This brings us back to the real problem that makes discussions of reaching this planet fundamentally premature. The target uncertainty is not a complication to acknowledge before proceeding to more interesting topics. It is the central barrier that renders all subsequent discussions speculative. We measured a shadow, we inferred a size. We attempted to measure mass and obtained only constraints. We know almost nothing about what exists at the location called Kepler-22b, except that something of a certain size orbits there. Every beautiful artist rendering depicts assumptions rather than observations. Every engineering analysis optimizes for scenarios that may not correspond to reality. Every calculation of travel time, mission duration, and resource requirements builds elaborate structures on foundations of ignorance. The planet remains undefined at the most fundamental level, not merely uncertain in detail but unknown in basic character. The difference between a rocky super-Earth and a gaseous mini-Neptune is not a matter of detail. It is a matter of whether the world has a surface or exists as boundless atmosphere all the way down. Until we can resolve what kind of planet Kepler-22b actually is, every subsequent question about reaching it lacks meaningful answers. The journey cannot be planned because the destination cannot be characterized. The destination cannot be characterized because the measurements required exceed current and near-future technological capability. And even if we somehow obtained complete characterization tomorrow, definitively establishing the planet's mass, composition, atmosphere, and surface conditions, the problems would only begin rather than end. Because between Earth and Kepler-22 stretches 640 light-years of void, a distance so vast that crossing it challenges not just current engineering but potentially the fundamental limits of what the laws of physics permit. 640 light-years. The number appears in every description of Kepler-22b, often stated matter-of-factly before discussions pivot to more emotionally engaging topics. Habitable zones capture imagination. Earth-like conditions generate headlines. The distance gets mentioned and then forgotten, treated as a mere detail rather than the defining characteristic that shapes every aspect of any potential journey. But this distance deserves far more attention than it typically receives. 640 light-years represents a gulf so vast that crossing it challenges not just current technology but potentially the fundamental limits of what might ever be achievable. The number sounds almost reasonable when spoken quickly. It becomes terrifying when you stop to comprehend what it actually means. Light travels at approximately 186,000 miles per second in the vacuum of space. Photons race along at this velocity without deviation, covering distances that dwarf human experience in mere moments. Light crosses the distance from Earth to the Moon in about 1.3 seconds. It spans the gulf between Earth and Sun in roughly 8 minutes. These timescales feel almost accessible, almost within the realm of human intuition, but light requires 640 years to travel from Kepler-22 to Earth. A photon that left that distant star when the Black Death was devastating medieval Europe would just now be arriving at our telescopes. The light we observe tonight began its journey before Columbus crossed the Atlantic, before the printing press transformed communication, before the scientific revolution reshaped human understanding of the cosmos. This cosmic speed limit represents the fastest possible rate at which anything can traverse space. Nothing moves faster, not information, not energy, not matter. Einstein's special relativity established this constraint over a century ago, and every experiment since has confirmed it without exception. The speed of light is not merely a current technological barrier waiting to be broken. It appears to be a fundamental feature of our universe's architecture. At this maximum possible velocity, a journey to Kepler-22b would require 640 years. A photon leaving Earth today would arrive at the Kepler-22 system around the year 2665. The travelers who departed would have descendants spanning more than 20 generations before arrival, assuming any biological connection remained meaningful across such timescales. But of course, we cannot travel at light speed. The physics of special relativity prohibit any massive object from reaching that velocity. As objects accelerate toward light speed, their relativistic mass increases without bound. Accelerating to 90% of light speed requires roughly twice the energy of accelerating to 80%. Accelerating to 99% requires roughly 7 times more energy than reaching 90%. The energy requirements climb toward infinity as velocity approaches the cosmic limit. Reaching light speed would require infinite energy, which is to say it would require more energy than exists in the observable universe. Even approaching light speed becomes progressively more expensive in ways that mock human ambitions. The cosmic speed limit is not merely difficult to reach, it is mathematically unreachable for anything with mass. The fastest spacecraft humanity has ever built achieved velocities that seem impressive until placed in interstellar context. The Helios probes launched in the 1970s reached approximately 157,000 miles per hour during close solar passes. Modern Parker Solar Probe has exceeded even these velocities, reaching speeds over 430,000 miles per hour at perihelion during its closest solar approaches. Parker moves faster than any human-made object in history. These achievements represent the pinnacle of human spaceflight engineering, the absolute best we have accomplished after decades of technological development. At Parker Solar Probe's maximum velocity, crossing 640 light-years would require approximately 930,000 years, nearly a million years of travel. Homo sapiens have existed for roughly 300,000 years. Human civilization with agriculture and permanent settlement spans perhaps 12,000 years. Written history covers around 5,000 years. The journey to Kepler-22b, at our fastest achieved speed, would require roughly 75 times longer than our entire species has existed. A spacecraft launched today at these record-breaking velocities would arrive so far in the future that predicting conditions on Earth becomes meaningless. Species evolve on such timescales, continents shift position, ice ages come and go multiple times. Whatever sent the spacecraft would bear no recognizable relationship to whatever might receive its transmissions upon arrival. This temporal scale reveals the first fundamental problem with discussing missions to Kepler-22b. We are not talking about space travel in any conventional sense of the term. We are discussing launching artifacts into temporal distances that exceed biological and civilizational continuity, messages in bottles cast into an ocean of time so vast that the concept of sender and receiver loses meaning. But perhaps faster propulsion could help. Perhaps technologies beyond our current capability might reduce these journey times to something more manageable. Let us examine the possibilities with unflinching honesty about what each actually offers. Chemical rockets have carried humanity to the moon and sent probes throughout our solar system. They represent mature, well-understood technology refined over more than 8 decades of development. The best liquid hydrogen and liquid oxygen combinations achieve exhaust velocities around 4.5 kilometers per second. This represents a fundamental thermodynamic limit based on the energy released by chemical bonds. The Tsiolkovsky rocket equation governs all reaction-based propulsion with mathematical precision. To achieve a target velocity, spacecraft require a specific ratio of initial mass to final mass. This ratio grows exponentially with desired velocity. Doubling your target velocity more than doubles your fuel requirement. It squares it. Tripling your velocity cubes the mass ratio. For interstellar velocities, chemical rocket fuel requirements become laughably absurd. Accelerating a 1 kilogram payload to merely 1% of light speed using chemical propulsion would require a starting mass exceeding the mass of the observable universe. This is not an engineering challenge to be solved with better materials or more efficient combustion. It is a mathematical impossibility built into the physics of chemical energy storage. Ion propulsion offers substantially better exhaust velocities, reaching tens of kilometers per second with current technology. Missions like Deep Space One and Dawn demonstrated that ion engines could accelerate spacecraft to higher velocities than chemical rockets alone, given sufficient time for their gentle thrust to accumulate. But ion engines produce thrust measured in fractions of a newton. The Dawn spacecraft's ion engine produced thrust equivalent to the weight of a few sheets of paper. This minuscule force operates continuously for months or years, gradually building velocity through patient accumulation. The approach works beautifully for solar system exploration, where journey times measured in years remain acceptable. Even with perfect performance over decades of continuous operation, ion propulsion might achieve perhaps 0.1% of light speed. The journey to Kepler-22b would still require 640,000 years, an improvement over chemical rockets by a factor of roughly 2, but still a duration that renders human involvement meaningless. Nuclear thermal propulsion increases exhaust velocity beyond what chemical reactions can achieve. The NERVA program in the 1960s demonstrated that nuclear reactors could heat hydrogen propellant to temperatures far exceeding chemical combustion. The superheated hydrogen expands through a nozzle at velocities roughly double what the best chemical engines achieve. Modern nuclear thermal designs might push exhaust velocities to 10 kilometers per second or beyond, but doubling or tripling exhaust velocity still leaves interstellar capability far beyond reach. The rocket equation's exponential nature means that modest improvements in exhaust velocity translate to modest improvements in achievable spacecraft velocity. Nuclear thermal rockets might enable exploration of the outer solar system with journey times measured in years rather than decades. They remain utterly inadequate for interstellar distances. Nuclear pulse propulsion represents a more radical approach. Project Orion in the 1950s and 60s studied the concept of riding nuclear explosions to high velocity. Small nuclear bombs would be ejected behind a spacecraft and detonated. A massive pusher plate would absorb the explosion's momentum, accelerating the ship through repeated blasts. Orion studies suggested that spacecraft could theoretically reach several percent of light speed through this method. Political and environmental concerns effectively ended the program, but the physics remained valid. Humanity possessed, at least theoretically, a propulsion concept capable of interstellar velocities. Even at 5% of light speed, a velocity that would require thousands of nuclear detonations and engineering far beyond current capability, the journey to Kepler-22b would require 12,800 years, longer than the span from the invention of agriculture to the present day. A mission launched when humans first began farming would be arriving now. A mission launched today would arrive when human civilization had transformed beyond recognition or ceased to exist entirely. More speculative propulsion concepts populate the scientific literature. Antimatter engines could theoretically convert mass directly to energy with perfect efficiency, achieving the highest possible exhaust velocities physics permits. When matter and antimatter meet, they annihilate completely, transforming into pure energy according to Einstein's famous equation. But antimatter production remains one of humanity's most challenging technical endeavors. Current facilities generate mere nanograms per year at costs measured in billions of dollars per gram. The total antimatter produced by humanity throughout history would not power a flashlight for more than a few seconds. Scaling production to quantities useful for propulsion requires advances so dramatic they border on fantasy. Laser-pushed sails offer another theoretical pathway. The breakthrough Starshot concept proposes using enormous ground-based laser arrays to accelerate tiny probes to 20% of light speed. At such velocities, the journey to Kepler-22b would require approximately 3,200 years. Still enormous by human standards, but approaching timescales where multi-generational missions at least become conceivable. The catch lies in the details. Starshot-class systems accelerate probes weighing mere grams, carrying only the most minimal instrumentation. Scaling this approach to spacecraft capable of meaningful scientific investigation requires proportionally more powerful lasers. A probe weighing kilograms rather than grams demands laser arrays vastly more powerful than anything humanity has built or seriously proposed building. Sending anything capable of carrying humans lies so far beyond current capability that serious discussion becomes impossible. The mass of human life support systems, radiation shielding, food production, and habitat structures exceeds gram-scale probes by factors of millions. The laser power required to accelerate such masses does not exist and would require planetary-scale engineering to create. Fusion propulsion tantalizes with theoretical promise. If controlled fusion reactions could be harnessed for spacecraft propulsion, exhaust velocities might reach several percent of light speed. The energy density of fusion fuel vastly exceeds chemical propellants, potentially enabling the extreme velocity changes interstellar travel demands. But humanity has struggled for 7 decades to achieve sustained controlled fusion for power generation on Earth, where conditions can be carefully managed and mass constraints do not apply. Compact fusion engines suitable for spacecraft remain even further from reality. The engineering challenges multiply when fusion reactors must be miniaturized, ruggedized for launch, and operated for decades without maintenance. Even assuming revolutionary propulsion breakthroughs, relativistic physics introduces complications that science fiction often glosses over. At velocities approaching significant fractions of light speed, time itself begins to behave strangely. Einstein's special relativity predicts that time passes more slowly for objects moving at high velocity relative to stationary observers. This time dilation effect becomes pronounced only at speeds approaching light velocity. Consider a spacecraft traveling at 90% of light speed. From the perspective of observers on Earth, the journey to Kepler-22b would require approximately 711 years, but for passengers aboard the spacecraft, time would pass more slowly by a factor of roughly 2.3. The travelers would experience only about 309 years of subjective journey time. This time dilation might seem like a benefit, reducing the experienced duration of interstellar voyages, but it creates asymmetries that complicate any notion of connection between travelers and their origin civilization. The travelers age slowly, while Earth ages quickly. A crew that departed at age 30 might arrive at age 339 by their own reckoning, while 711 years had passed on Earth. At even higher velocities, the effects become more extreme. At 99% of light speed, time dilation produces a factor of roughly 7. Travelers would experience 1 year for every 7 years passing on Earth. At 99.9%, the factor exceeds 22. The subjective journey time shrinks dramatically while the objective duration remains constrained by distance and velocity. But achieving such velocities requires energy expenditure that scales toward infinity as light speed approaches. The relativistic mass increase that prevents reaching light speed also increases the energy needed for each incremental velocity gain. The time dilation benefit comes at exponentially increasing cost. You cannot cheat physics through clever engineering. Furthermore, time dilation does nothing to solve the problems facing the spacecraft itself. While human passengers might experience compressed subjective time, the ship's mechanical and electronic systems experience the full objective duration. Radiation damage accumulates based on objective time exposure, not subjective experience. Material fatigue develops over objective years, not dilated years. The systems that keep passengers alive must function for the full journey duration regardless of how quickly time passes for biological occupants. This brings us back to the real problem that shadows all discussion of propulsion to Kepler-22b. Every technology that might conceivably cross interstellar distances operates on timescales that transform the meaning of mission planning itself. Consider what happens to any spacecraft during a journey lasting thousands of years. No human-built system has ever operated reliably for such durations. The oldest functioning machines on Earth measure their ages in centuries at most, and these are simple mechanical devices like clocks, not complex electronic systems capable of navigation and communication across interstellar distances. Electronic components degrade continuously under cosmic radiation bombardment. High-energy particles strike semiconductor materials, creating defects that accumulate over time. Each particle impact can flip bits in memory, corrupt processing logic, or create permanent damage to circuit pathways. Spacecraft designed for decades-long missions require radiation-hardened components and redundant systems to survive. Extending design lifetime from decades to millennia requires reliability improvements we do not know how to achieve. The interstellar medium itself poses hazards absent within our solar system's protective bubble. The heliosphere, the region of space dominated by the solar wind, shields the inner solar system from much of the galactic cosmic radiation that permeates interstellar space. A spacecraft traveling to Kepler-22b would spend the vast majority of its journey outside this protective envelope, exposed to radiation levels substantially higher than anything our solar system probes have encountered. Micrometeorite impacts present another cumulative hazard. While individual dust particles pose minimal threat, their effects accumulate over millennia of travel. A spacecraft moving at even modest interstellar velocities transforms tiny dust grains into high-energy projectiles. Each impact erodes surface materials, degrades thermal coatings, pits optical surfaces, and risks penetrating pressure vessels. Over thousands of years, billions of such impacts would sandblast any exposed surface. Mechanical components face their own degradation pathways, independent of external hazards. Lubricants evaporate into vacuum or polymerize into useless solids over long timescales. Bearings wear despite minimal use as atomic scale irregularities gradually enlarge. Seals degrade and leak as polymer chains break down. Metal components develop fatigue cracks from thermal cycling as the spacecraft rotates to distribute solar heating or adjusts orientation for navigation. The probability of catastrophic failure accumulates year after year across millennia of travel. Even systems designed with extreme redundancy eventually exhaust their backup capabilities. A mission with 99% reliability per year would have less than 1/1,000,000th of 1% chance of surviving 10,000 years. The mathematics of accumulated failure probability doom any conceivable design over such timescales. Power generation presents perhaps the most fundamental challenge for ultra-long-duration missions. Every spacecraft system requires electrical power to function. Navigation computers need power. Communication systems need power. Life support needs power. Even passive systems like thermal control eventually require powered intervention to maintain acceptable conditions. Solar panels become useless beyond the outer solar system where sunlight dims to insignificance. Within a few hundred astronomical units of the Sun, solar intensity drops below levels capable of powering meaningful spacecraft operations. The journey to Kepler-22 spans distances measured in millions of astronomical units. Solar power is simply not an option for more than the tiniest fraction of the journey. Nuclear power systems offer the only currently viable alternative for deep space missions. Radioisotope thermoelectric generators have powered spacecraft for decades, converting the heat from radioactive decay into electricity. The Voyager probes continue operating more than 45 years after launch, using plutonium-238 power sources. But radioisotope generators produce diminishing power as their fuel decays. Plutonium-238 has a half-life of roughly 87 years. After 174 years, only 1/4 of the original power remains. After 348 years, only 1/16th. A generator sized to provide adequate power at launch would produce negligible output within a few centuries. Far short of the millennia required for interstellar transit, nuclear fission reactors could theoretically provide power for longer durations, but they introduce complexity, mass, and failure modes that compound the challenges already discussed. Reactors require control systems, cooling systems, and radiation shielding, all of which must function flawlessly for millennia. No reactor has ever operated for more than a few decades. Expecting thousand-year operation assumes reliability improvements of several orders of magnitude. Fusion reactors might offer better power density and longer operational lifetime if the technology could be made to work at spacecraft scales, but we have not achieved sustained fusion power generation at any scale, let alone compact systems suitable for interstellar vehicles. Betting mission success on technology that does not exist compounds speculation upon speculation. Energy storage presents equally daunting challenges. Even if power generation could be maintained, storing energy for periods of high demand or emergency operations requires technologies that degrade over time. Batteries lose capacity through chemical processes that cannot be entirely prevented. Capacitors leak charge through imperfect insulators. Flywheels slow through bearing friction that accumulates over millennia. No energy storage technology maintains full capability for thousands of years. Life support for human passengers multiplies these challenges beyond recognition. Maintaining breathable atmosphere requires either enormous stored reserves or biological recycling systems that function perfectly for millennia. A closed ecosystem capable of recycling air, water, and nutrients indefinitely has never been demonstrated even for periods of years, let alone centuries or millennia. Temperature control demands power systems that operate without failure for longer than any civilization has existed. Humans require environmental temperatures within a narrow range compared to the extremes of space. Maintaining that range requires continuous active management, heating in the cold of interstellar void, cooling to reject metabolic and electronic waste heat. Any interruption in thermal control would prove fatal within hours or days. Food production for crews measured in thousands over journeys measured in millennia staggers calculation. Storing sufficient food proves impossible given reasonable mass constraints. Growing food requires agricultural systems that function without degradation across timescales that exceed the entire history of agriculture itself. Every crop failure, every pest outbreak, every soil depletion event that might occur once per century becomes statistically certain over 10,000-year journeys. The longest crewed space mission in history lasted approximately 437 days, achieved by Valery Polyakov aboard the Mir space station. This remarkable endurance record required constant resupply from Earth and continuous maintenance by the crew. Extending such missions to thousands of years without any external support exceeds any engineering capability humanity has demonstrated or can currently conceive. Cryogenic preservation appears throughout science fiction as a solution to the human duration problem. Freeze the passengers before departure, maintain them in suspended animation throughout the journey, revive them upon arrival. The millennia of travel would pass in dreamless unconsciousness, effectively instantaneous from the traveler's perspective, but cryogenic preservation of humans does not currently work. Large mammals, cooled to temperatures necessary for long-term preservation, suffer cellular damage from ice crystal formation that proves fatal upon warming. Water expands when it freezes, rupturing cell membranes and destroying tissue structure. Cryoprotectant chemicals can reduce this damage but cannot eliminate it. No human or large mammal has ever been cooled to cryogenic temperatures and successfully revived. The biological challenges extend beyond ice crystal damage. Neural connections that encode memory and personality may not survive the freezing and thawing process. Synaptic structures are delicate, dependent on precise molecular arrangements that freezing disrupts. Even if a body could be revived, the person who entered suspension might not be the person who emerges. The philosophical questions surrounding identity continuity through cryogenic preservation remain unanswered because the basic biological feasibility remains undemonstrated. Generation ships represent an alternative approach that avoids the cryogenic challenge by accepting that travelers will live and die during the journey. Multiple generations would be born, mature, reproduce, and pass away aboard the vessel. The descendants of the original crew would eventually arrive at the destination, carrying whatever cultural memory of Earth survived the voyage. But maintaining a functioning society across hundreds of generations confined to a spacecraft presents challenges that may exceed even the engineering difficulties. Every human social structure in history has transformed dramatically over periods far shorter than interstellar journey times. Religions rise and fall, languages evolve beyond mutual comprehension, political systems cycle through phases, cultural values shift in ways that would be unrecognizable to earlier generations. Consider what has happened to human societies over merely 500 years, a tiny fraction of the journey time to Kepler-22. The political structures of 1520 bear almost no resemblance to those of 2020. The religious landscape has transformed through reformations, revivals, and secularization. Languages have evolved so substantially that speakers of modern English struggle with texts from that era. Every aspect of social organization has been revolutionized multiple times. A generation ship would need to maintain not just biological populations, but cultural continuity and mission focus across timespans exceeding all recorded history. The crew who arrive at Kepler-22b would share genetic heritage with the crew who departed Earth, but might share nothing else. Their language, beliefs, social organization, and understanding of the mission might have evolved beyond all recognition. What would keep a society focused on a mission that none of its members chose, that their ancestors chose for them hundreds of generations past? How would mission knowledge be transmitted across linguistic and cultural evolution that transforms meaning over centuries? What social structures could maintain stability in permanent confinement without the release valves of immigration, expansion, or contact with other societies? Human societies have never existed in permanent isolation with zero possibility of outside contact or expansion. Every historical society has had neighbors, trading partners, enemies, or frontiers. The psychological and sociological effects of permanent total isolation over hundreds of generations remain unknown because no analog exists. We cannot extrapolate from any human experience to conditions that have no precedent. The population required to maintain genetic diversity across such timescales adds another constraint. Avoiding inbreeding depression over hundreds of generations requires starting populations measured in thousands rather than dozens. Genetic modeling suggests minimum viable populations of roughly 5,000 individuals to maintain diversity over multi-generational timescales, with larger populations providing additional buffer against random genetic drift. Housing thousands of humans in a self-sustaining spacecraft for millennia demands structures of unprecedented scale, complexity, and reliability. Each person requires living space, atmospheric volume, food production capacity, water recycling capability, and waste processing systems. Multiply these requirements by thousands of individuals, then by hundreds of generations, and the mass and energy requirements exceed anything humanity has seriously contemplated building. No matter how advanced our propulsion systems become, these fundamental realities remain unchanged. 640 light-years represents a distance that transforms space travel into something unlike any activity humans have ever undertaken. The civilization that launches such a mission would not be the civilization that receives reports of its outcome. The entire context that gave the mission meaning would dissolve during the journey. All of this still fails, because we return to the central problem haunting this entire discussion. Even if we solved every propulsion challenge, every reliability requirement, every life support necessity, we would still be sending spacecraft toward a target we cannot define. The journey time calculations assume we know our destination in sufficient detail to plan arrival, but as established earlier, we do not know what Kepler-22b actually is. We measured a shadow and inferred a size. We lack the mass, composition, atmosphere, and surface information that mission planning requires. The propulsion discussions proceed as if a known target awaits, when in fact only uncertainty awaits. The navigation challenges across interstellar distances compound this fundamental problem. Kepler-22b orbits its star with a period of approximately 290 days, over 12,800 years of travel at 5% light speed. The planet completes over 16,000 orbits. The position where the planet exists when the spacecraft departs differs entirely from the position where it exists when the spacecraft might arrive. Calculating where the planet will be after 16,000 orbits requires predicting orbital dynamics with extraordinary precision. Any uncertainty in the orbital period multiplied by 16,000 cycles produces positional uncertainty measured in millions of kilometers. The spacecraft must aim not at where the planet is, but at where the planet will be, after a duration exceeding recorded human history. The star itself moves through the galaxy. Kepler-22 travels through space relative to our Sun, at velocities measured in kilometers per second. Over millennia, this motion accumulates to distances measured in light years. The star's position when you aim differs substantially from its position when you arrive. Predicting stellar motion requires understanding gravitational perturbations from neighboring stars, galactic rotation effects, and velocity components that current measurements constrain only approximately. Our own Sun moves as well. The departure point shifts continuously throughout the journey. The relative geometry between origin and destination changes in ways that must be predicted with extraordinary precision for any hope of successful arrival. For a journey lasting 13,000 years, navigational errors accumulate catastrophically. Small uncertainties in initial trajectory compound over millennia into enormous positional errors at destination. You must predict where a star will be located after a time span exceeding human civilization's existence. You must account for gravitational perturbations from every massive object the spacecraft encounters along its path. The accumulated uncertainties in such predictions might well exceed the size of the entire planetary system you aim to reach. Mid-course corrections require knowing your position and velocity with precision sufficient to calculate necessary adjustments. But determining position in interstellar space poses challenges absent within the solar system. No GPS satellites mark interstellar coordinates. Stellar parallax measurements require precisely known reference frames that shift over the journey duration. The navigation problem may be as intractable as the propulsion problem for journeys of sufficient duration, but even perfect navigation fails because we still do not know what awaits at the destination. We might send a spacecraft optimized for landing on a rocky super-Earth and discover upon arrival that Kepler-22b is a mini-Neptune with no surface. We might design for high gravity and encounter an ocean world with moderate gravity but global seas. We might prepare for thick atmosphere and find thin atmosphere or no atmosphere at all. No matter how advanced our engines become, this fundamental truth remains. We cannot calculate arrival parameters without knowing what gravity well we approach. We cannot design landing systems without understanding what surface or atmosphere awaits. We cannot plan surface operations without knowing whether a surface exists. The target uncertainty does not merely complicate mission design, it makes mission design meaningless. We cannot optimize for unknown conditions. We cannot prepare for uncharacterized environments. We cannot plan arrivals at undefined destinations. The distance problem and the characterization problem compound each other into something worse than either alone. We cannot characterize the target because it lies too far away for detailed observation. We cannot reduce journey time enough to allow adaptive mission planning. We cannot receive feedback during the journey to modify our approach. We launch in ignorance and arrive in ignorance, separated by millennia during which nothing can change. The journey to Kepler-22b is not merely difficult, it may be conceptually incoherent given current knowledge. The question of how long it would take assumes that meaningful travel is possible in principle, but travel to an undefined destination through a duration exceeding civilizational continuity may not qualify as travel in any meaningful sense. We approach something closer to launching time capsules toward coordinate locations where something exists without knowing what that something is. The artifacts might arrive, they would find whatever conditions actually prevail at that location. Whether those conditions match any design assumptions remains pure chance. This brings us back to the real problem that makes all propulsion discussions ultimately secondary. Even if humanity developed propulsion capable of reaching Kepler-22b within a single human lifetime, the target uncertainty would remain. Even if we could depart tomorrow and arrive next week, we would not know what we were traveling to. The distance creates one category of impossibility measured in time. The characterization gap creates a different category of impossibility measured in knowledge. Together, they form a doubly impossible problem that neither propulsion advances nor extended patience can resolve. Every calculation of journey time proceeds from assumptions that cannot be validated. Every discussion of generation ships, cryogenic suspension, and relativistic travel builds elaborate structures on foundations of profound uncertainty. 640 light-years of void separate Earth from Kepler-22b. Crossing that void requires technologies that do not exist and may never exist. Surviving that crossing requires capabilities that exceed all human achievement. Arriving at that crossing's end would deliver spacecraft to a destination that remains fundamentally unknown despite more than a decade of observation with humanity's most sophisticated instruments. The distance is not merely an engineering challenge, it is a barrier that transforms the nature of the endeavor itself. At 640 light-years, we transition from space exploration to something for which humans have no framework and no experience. We enter a realm where the questions we know how to ask may not be the questions that matter, and even acknowledging all these barriers, the deepest problem awaits examination. The question of how long it would take to reach Kepler-22b rests on assumptions that collapse when examined carefully. The question itself may be malformed in ways that prevent any meaningful answer from existing. The question appears simple enough. How long would it take to reach Kepler-22b? Humans have asked similar questions throughout the history of exploration and received meaningful answers. How long to cross the Atlantic? Weeks by sailing ship, hours by aircraft. How long to reach the moon? About 3 days with Apollo-era technology. How long to reach Mars? 6 to 9 months depending on orbital alignment. These questions have answers because the destinations exist as defined targets with known properties. But the question about Kepler-22 differs fundamentally from every exploration question humanity has previously asked. It asks about reaching something we cannot define. It assumes knowledge we do not possess. It treats as solved problems that remain unsolved. And when you probe this difference carefully, following the logic to its necessary conclusions, the entire question structure collapses into meaninglessness. What exactly do we mean by reach in this context? The word seems obvious until you try to specify its meaning for an unknown destination. For the moon, reaching meant landing humans on a solid surface, conducting exploration activities and returning safely to Earth. The moon's properties were known with sufficient precision to design spacecraft for lunar conditions. We knew the gravity, the surface composition, the absence of atmosphere, the temperature extremes. Reaching meant arriving prepared for known conditions and accomplishing defined objectives. For Mars, reaching has meant different things across different missions. Orbital photography constitutes one form of reaching. Surface rovers represent another. Potential human landing sites would constitute yet another definition of successful arrival. But in every case, we knew enough about Mars to design appropriate systems. We understood the thin carbon dioxide atmosphere, the rusty iron oxide surface, the gravitational pull, the temperature ranges. Mission designers could make concrete decisions based on measured planetary properties. For Kepler-22b, we cannot define what reaching means because we do not know what kind of world exists at that location. The word reaching assumes a destination with properties that can be engaged. Landing means nothing if no solid surface exists. Orbital insertion calculations require planetary mass we have not measured. Atmospheric entry might be possible, or might be instantly fatal depending on conditions that remain entirely unknown. The question how long to reach Kepler-22b assumes we can specify what reaching would entail. We cannot. The question assumes we know our destination well enough to plan an arrival. We do not. The question treats the journey as the primary unknown while taking the destination as given. In reality, the destination itself constitutes the fundamental unknown that makes all subsequent questions premature. Consider what happens when you try to answer the reaching question seriously. You must first decide what kind of arrival counts as reaching. Landing on a surface? What if no surface exists? Entering orbit? At what altitude given unknown planetary mass? Passing through the system? That hardly qualifies as reaching in any meaningful sense. Deploying atmospheric probes? Into what kind of atmosphere? Every possible definition of reaching requires assumptions about what exists at the destination. The question cannot be answered without first answering a more fundamental question that we cannot currently address. What is Kepler-22b? This logical dependence reveals the malformed nature of the original question. We have asked about the journey without establishing that a coherent destination exists. We have inquired about travel time without knowing what we travel toward. We have treated as straightforward a question that contains hidden assumptions we cannot validate. The problem resembles asking how long it takes to reach the treasure marked on a map that shows only coordinates with no indication of what exists at that location. Perhaps the treasure lies in an accessible valley. Perhaps it sits atop an unclimbable cliff. Perhaps the marked location contains only ocean with no land at all. The journey time depends entirely on what conditions await at the destination, and the map provides no such information. Kepler-22b offers us celestial coordinates where something exists. Every journey time calculation implicitly assumes a particular destination type and designs for that assumption. But the assumption might be entirely wrong. We might calculate travel time to a rocky super-Earth and find a mini Neptune awaiting our arrival. We might design for one planetary type and encounter something completely different. This brings us back to the real problem that has haunted every section of this discussion. The target uncertainty does not merely complicate our calculations, it invalidates them entirely. We are not computing how long to reach Kepler-22b, we are computing how long to reach various imaginary versions of that world that might or might not correspond to whatever actually exists, 640 light-years away. The distinction matters because mission planning is not abstract speculation. It requires concrete decisions about specific hardware. Engineers must choose materials based on expected thermal environments. They must size structural components based on anticipated gravitational loads. They must design power systems based on predicted energy availability. They must configure communication systems based on assumed signal path characteristics. Every decision flows from understanding of the destination conditions that will be encountered. Without that understanding, mission planning becomes an exercise in imagination rather than engineering. You design not for what exists, but for what you hope exists, fear exists, or simply decide to assume exists. The resulting spacecraft reflects your assumptions far more than any objective reality at the destination. You have designed for an imaginary world that shares only coordinates with the actual world awaiting arrival. All discussions about propulsion systems, journey times, generation ships, cryogenic suspension, and relativistic travel tacitly assume that the destination problem has been solved. They proceed as if we know enough about Kepler-22b to design appropriate hardware for arrival. They take for granted that the planet will match our expectations closely enough that our preparations will prove adequate. These assumptions have no foundation whatsoever in measurement or observation. Consider the practical implications of this logical collapse. No responsible space agency would approve a mission to an undefined target. The review processes that govern major missions require detailed destination characterization before hardware design can proceed. Scientists must demonstrate understanding of target conditions before engineers can design systems to survive those conditions. You cannot build something to work somewhere if you do not know what that somewhere is like. No reasonable engineer would design systems for completely unspecified conditions. Engineering requires constraints. Material selection depends on thermal environment. Structural design depends on load expectations. Power systems depend on available energy sources. Communication systems depend on distance and interference environment. Without constraints, design becomes impossible. With wrong constraints, design becomes futile. No sensible planner would allocate resources to reach somewhere that might not be what expected. Every mission competes with other missions for funding, personnel, and institutional attention. Missions must demonstrate feasibility and scientific return to justify their costs. A mission to an undefined destination cannot demonstrate feasibility because the conditions for success cannot be specified. Yet popular discussions of reaching Kepler-22 routinely skip past these fundamental objections. The target uncertainty gets mentioned briefly, if at all, before exciting speculation about interstellar propulsion and human colonization proceeds. The problems are treated as minor complications rather than mission-ending obstacles. The question gets asked as if it had an answer, when the question itself is malformed. This pattern reflects something deep about human psychology and our relationship with cosmic possibilities. We want there to be Earth-like worlds awaiting human footsteps. We want interstellar travel to be possible in principle, even if difficult in practice. We want the question of how long to reach distant planets to have answers measured in years or centuries rather than in fundamental impossibilities. But wanting does not make it so. The universe is not obligated to provide accessible destinations for human expansion. Distant worlds are not required to match our expectations or hopes. Questions are not guaranteed to have meaningful answers simply because we wish to ask them. The discovery of Kepler-22b represents a genuine scientific achievement that deserves celebration. Finding a planet-sized object orbiting in the habitable zone of a sun-like star at such enormous distance pushed observational astronomy to remarkable limits. The detection is real. The planet exists. Something orbits Kepler-22 at the distance and period the transit data revealed, but discovery and characterization are fundamentally different activities. We discovered that something exists at a specific location. We have not characterized what that something is. The gap between detection and understanding spans the entire difference between knowing a shadow exists and knowing what cast that shadow. We have accomplished the former, we have not accomplished the latter. Future observations might change this situation. Next-generation telescopes with larger primary mirrors and more sensitive instruments might detect the planet's mass through more precise radial velocity measurements. The 30-meter class observatories under construction could potentially push measurement precision low enough to extract a definitive mass signal from the stellar wobble data. Advanced spectroscopic techniques might reveal atmospheric composition if planetary geometry ever allows transmission observations during transit. Space-based telescopes optimized for exoplanet characterization might achieve the contrast ratios needed to separate planet light from stellar glare. Perhaps, but these possibilities remain speculative. The technical challenges are formidable. The timeline for meaningful results stretches to decades at minimum, quite possibly much longer. The researchers who might finally characterize Kepler-22b have not yet begun their careers. The instruments that might enable that characterization have not yet been designed. In the meantime, we have what we have: a shadow measurement, a size estimate, an orbital period, an upper limit on mass, a location in space, almost nothing about what actually exists at that location. This brings us back to the real problem that no amount of propulsion development can solve. Even if humanity developed engines capable of reaching Kepler-22b within a single human lifetime, the target uncertainty would remain. Even if we could depart tomorrow and arrive next week, we would not know what we were traveling toward. The journey is not the only problem. The destination is equally problematic, and in some ways more fundamentally so. The collapse of the question extends deeper than practical mission planning into fundamental questions about knowledge and its limits. What does it mean to know that a destination exists when we cannot characterize that destination? What does it mean to plan a journey when the endpoint remains undefined? What does it mean to ask how long something takes when the something cannot be specified? In normal usage, a destination is somewhere you can describe. It has properties you can list. It would look a certain way if you arrived and photographed it. The Moon is a rocky, airless body with specific surface features. Mars is a cold desert world with thin atmosphere and rusty soil. Jupiter is a gas giant with no solid surface but spectacular atmospheric bands and a system of diverse moons. Kepler-22b fails every test for destination status. We cannot describe it beyond shadow dimensions and orbital characteristics. We cannot list its properties because we have not measured them. We cannot say what it would look like because it might look like any of countless different things depending on composition we cannot determine. The planet exists in a strange state unlike any destination humans have previously considered reaching. We know something is there, we cannot say what that something is. We have discovered without characterizing, we have detected without understanding, we have found without knowing what we found. This state challenges assumptions built into the very structure of the question about reaching it. Questions about journey time assume we know enough about destinations to meaningfully ask about arrivals. We do not meet this assumption. Questions about reaching assumed destinations exist as defined targets. Kepler-22b does not meet this criterion. Questions about travel time assume the journey constitutes the primary unknown. For Kepler-22b, the destination itself is the unknown that prevents all subsequent questions from having meaningful answers. No matter how advanced our propulsion systems become, this fundamental truth remains. We cannot calculate arrival parameters without knowing what gravity well we approach. We cannot design landing systems without understanding what surface or atmosphere awaits. We cannot plan surface operations without knowing whether a surface exists. The target uncertainty does not merely add error bars to our calculations. It eliminates the possibility of meaningful calculation altogether. Every number we might compute for journey time, fuel mass, mission duration, or arrival velocity assumes a specific planetary type that we have not confirmed exists. The calculations describe journeys to imaginary worlds, not to Kepler-22b, as it actually is. Consider what this means for the question that titles this discussion. How long would it really take to reach Kepler-22b, if it even exists? As we think, the qualifying phrase acknowledges the problem we have explored throughout this discussion. The planet might not exist as we think because we do not actually know what it is. And if we do not know what it is, we cannot meaningfully ask how long it takes to reach it. The answer to the title question is not a number of years or centuries or millennia. The answer is that the question cannot currently be answered because it asks about reaching something that has not been defined. The question collapses before any calculation can proceed. It assumes solved problems that remain unsolved. It treats as given what remains unknown. It asks the wrong thing. The right question is not how long to reach Kepler-22b. The right question is what is Kepler-22b? Until we can answer the second question with measurements rather than speculation, the first question remains meaningless. Journey time becomes relevant only after destination characterization establishes what we journey toward. This conclusion might seem pessimistic, but it reflects honest assessment of current knowledge rather than arbitrary limitation of human potential. We should celebrate the discovery that revealed Kepler-22b's existence while acknowledging how little that discovery told us about the planet itself. We should pursue the technological development that might eventually enable interstellar travel while admitting that propulsion alone cannot solve the destination problem. We should maintain wonder about distant worlds while recognizing that wonder and knowledge are different things. The human desire to explore beyond our world represents something admirable in our species. We look up at the stars and feel pulled toward that vast darkness. We discover distant worlds and imagine what standing on their surfaces might feel like. This imagination drives scientific progress and technological development in ways that benefit humanity, even when specific destinations remain forever beyond reach. But imagination divorced from knowledge produces fantasy rather than planning. We can imagine reaching Kepler-22b. We can write stories about what colonists might find there. We can create beautiful artwork depicting Earth-like oceans and verdant continents beneath an alien sun. None of this constitutes preparation for actual exploration, because actual exploration requires actual knowledge of actual destinations. The gap between imagination and capability has never been wider than in discussions of reaching exoplanets. We imagine interstellar voyages while lacking ability to send humans beyond low Earth orbit for more than brief visits to the moon. We depict Earth-like worlds while knowing almost nothing about what distant planets actually contain. This gap deserves acknowledgement rather than obscurement. Honesty about current limitations does not diminish human potential. It clarifies what must be accomplished before speculation becomes planning. Acknowledging that we cannot currently answer the question how long to reach Kepler-22b does not mean we will never be able to answer it. It means we have work to do before the question becomes meaningful. That work begins not with propulsion systems or life support technology, but with the far more difficult task of characterizing distant worlds. We need telescopes capable of measuring exoplanet masses through radial velocity or other techniques. We need instruments capable of detecting atmospheric composition through transmission or direct spectroscopy. We need observational programs patient enough to accumulate the data that planetary characterization requires. Only after such programs succeed can we meaningfully ask about journeys to specific destinations. Only with characterized targets can engineers design appropriate systems. Only with known conditions can planners assess feasibility. The sequence matters. Destination knowledge must precede journey planning because journey planning depends on destination knowledge. Kepler-22b represents just one world among thousands discovered in the past 2 decades. The Kepler mission alone confirmed more than 2,700 exoplanets before its retirement. The TESS mission continues adding discoveries. Ground-based surveys contribute additional finds. The catalogue of known worlds beyond our solar system now numbers in the thousands and grows steadily larger. Yet for all this abundance, the situation we have explored for Kepler-22b repeats across virtually the entire catalogue. We detect worlds through their shadows or their gravitational tugs. We measure sizes and orbital periods. We occasionally constrain masses. The universe has revealed itself to be filled with planets. Worlds orbit nearly every star. Planetary systems appear to be the norm rather than the exception. The raw material for countless potential destinations exists in staggering abundance throughout the galaxy, and presumably throughout the cosmos. But detection and characterization remain fundamentally different challenges. We have solved the first far more completely than the second. We can find planets. We struggle to understand what we have found. The discovery phase of exoplanet science has succeeded spectacularly. The characterization phase has barely begun. This asymmetry shapes everything about humanity's relationship with distant worlds. We know they exist by the thousands. We understand almost none of them well enough to plan meaningful visits. The catalogue of destinations grows while the catalogue of characterized destinations remains nearly empty. For the question of how long it takes to reach any of these worlds to become meaningful, this asymmetry must be resolved. Characterization must catch up with discovery. Understanding must follow detection. The shadows we have measured must be connected to the worlds that cast them. This process will require decades at minimum, quite possibly longer. The technical challenges are immense. The resources required are substantial. The patience demanded exceeds what scientific funding cycles typically provide. But without this investment, every detected exoplanet remains what Kepler-22b remains today, a coordinate in space where something exists without our knowing what that something is. 640 light-years away, something orbits a sun-like star in the habitable zone. We detected its shadow crossing the stellar disk multiple times at regular intervals. We measured its approximate size from the depth of the transit signal. We established upper limits on its mass through radial velocity observations that produced constraints rather than detections. We know almost nothing else about it with any confidence. Every journey time calculation, every mission scenario, every artistic rendering of blue oceans and green continents represents speculation built on assumptions we cannot verify. The beautiful images capture human hopes rather than scientific knowledge. The travel time estimates describe journeys to imaginary destinations rather than to whatever actually exists at those coordinates. The universe has given us a question wrapped inside another question. Kepler-22b exists. But as what? A rocky super-Earth with crushing gravity? A mini-Neptune with no surface to reach? An ocean world with global seas and exotic ice phases in the depths? Something else entirely that we lack categories to imagine? Until we can answer this deeper question, all surface questions about reaching the planet remain premature. The question of how long it would take to reach Kepler-22b collapses, not because interstellar travel is impossible, though it might be for all practical purposes, but because the destination itself remains undefined. We cannot ask meaningful questions about journeys to somewhere until we know what that somewhere actually is. What would it take for the question to become answerable? The requirements form a daunting list. First, we would need definitive mass measurement, transforming the upper limit constraint into an actual value with reasonable precision. This alone might require decades and instruments not yet built. Second, we would need atmospheric characterization sufficient to determine whether gas, liquid, or solid surfaces dominate. Third, we would need surface or cloud-top temperature measurements to understand the thermal environment awaiting any arriving spacecraft. Fourth, we would need radiation environment assessment to design appropriate shielding. Fifth, we would need rotation rate and axial tilt measurements to understand daylight cycles and seasonal variations. Only after satisfying these prerequisites could the question of journey time become meaningful. Only then could engineers design systems for known conditions rather than assumed ones. Only then could the question how long to reach Kepler-22b receive an answer that refers to the actual planet rather than imaginary versions of it. The timeline for achieving such characterization defies confident prediction. It depends on technological developments that have not occurred, funding decisions that have not been made, and scientific breakthroughs that cannot be scheduled. Optimistic scenarios suggest decades. Realistic scenarios suggest longer. Pessimistic scenarios suggest the characterization we need may never be achievable for targets at this distance. In the end, Kepler-22b teaches us as much about human limitations as about cosmic possibilities. We can detect worlds we cannot characterize. We can discover what we cannot understand. We can point to places in the sky where something exists, while remaining ignorant of what that something is. Our reach has exceeded our grasp, but not in the hopeful sense that phrase usually conveys. We have reached out to touch a distant world and found we cannot yet close our fingers around any understanding of what we have touched. The cosmos has revealed its abundance while concealing its details. Planets exist everywhere we look. Understanding eludes us almost everywhere we look. The gap between detection and comprehension defines our current relationship with the universe beyond our solar system. The answer to how long it would take to reach Kepler-22b is not a number. The answer is that the question cannot be meaningfully answered with current knowledge because the destination required to give the question meaning has not been established. Perhaps someday we will know enough about this distant world to ask properly about journeys there. Perhaps someday propulsion technology will advance enough to make such journeys conceivable on reasonable timescales. Perhaps someday the question will have an answer. That day has not arrived. Today we have a shadow measurement of an undefined world lying across a void so vast that current propulsion concepts cannot meaningfully address it. Even if we knew what awaited at the far side, today, the question about reaching Kepler-22b collapses before it can be answered because the destination itself remains a mystery, wrapped in starlight and imagination and hope. We have discovered something. We do not know what. We would like to reach it. We cannot plan how. We ask how long the journey would take. The question dissolves upon examination. This dissolution is not failure, it is clarity. It shows us where we actually stand rather than where we wish we stood. It reveals what must be accomplished before speculation becomes planning. It demonstrates that the hardest part of reaching distant worlds might not be the reaching but the knowing what we reach toward. The journey to Kepler-22b, if it ever becomes possible, will begin not with rocket engines or generation ships, but with the patient accumulation of knowledge about what exists at our intended destination. The first steps toward that distant world are not steps through space, but steps through understanding. We must learn what we are traveling to before we can meaningfully ask how long the traveling takes. Until then, the question remains what it has been throughout this discussion, not a question awaiting an answer, but a question awaiting the knowledge that would make answering possible. 640 light-years away, something waits. We do not know what, and until we do, asking how long it takes to reach it is asking a question that cannot yet be asked. We stand at the edge of knowledge, gazing across an immensity we can measure but not cross, toward a world we can detect but not describe. The question we most want to answer remains beyond our current ability even to properly ask. Perhaps future generations will look back at our time as the era when humanity first glimpsed the abundance of worlds but could not yet understand them. Perhaps they will have the tools we lack, the knowledge we seek, the capability to transform questions that collapse for us into questions with meaningful answers. Until that day arrives, we do what we can with what we have. We build better telescopes, we develop more sensitive instruments, we accumulate data point by patient data point, we push the boundaries of detection ever outward, while working to deepen the characterization that transforms detections into understood destinations. The work continues, the questions await, the universe keeps its secrets while slowly, painstakingly, we learn to ask the right questions in the right order. What is Kepler-22b? We do not yet know, but the asking itself represents progress. The recognition that this question must precede all others represents wisdom. The patience to seek answers before assuming them represents scientific maturity. Somewhere 640 light-years distant, a world orbits in the habitable zone of a sun-like star. We found it. We measured its shadow. We wait to learn what casts that shadow. The journey begins with knowledge. Everything else follows from that.